In section 5.1, we're going to be talking about area and summation notation, and we'll eventually connect these ideas back to our antiderivatives, which we talked about in that last section. So I'm going to start by giving you summation or sigma notation, which is really just a compact way of describing sums. So we use the Greek letter sigma to indicate a sum, and that's kind of a generic sigma notation, but let's take a look at a specific example. It might be a little bit easier to understand what is this notation telling us. Okay, so in my example, I've got sigma, and then you can see at the bottom this I equals 1, and at the top 5. And so what that is telling me is I am going to take the numbers 1 through 5, just whole numbers, always whole numbers, so just 1, 2, 3, 4, and 5. I'm going to plug them into this expression here, the I squared, and add them together. Okay, so we're taking the sum of I squared from 1 to 5. So in the expanded form, what that looks like is we have 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and then we add them all together. I ended up getting 55 for that sum. All right, so the number on the bottom tells us where we start, the number on the top tells us where we stop, and then inside the sigma is the function that we're working with. Here's another one, just to show you another example of this notation. So I equals 1 to 6, so we're starting at 1. We're stopping at 6. We always just go up by whole numbers. So 1, 2, 3, 4, 5, 6. And we're plugging those numbers in to I divided by 6. So 1, 6, 2, 6, 3, 4, 6, 5, 6, 6, 6. We add them all together. I got 21 over 6, or 7 halves. All right, so we're going to be doing some math with these sums, and so I need to give you a couple properties of sums. And so the first property I have written down says if you have the sum of a constant times a function, so this k right here is a constant. If you have a constant times a function, you can pull that k out front. This is basically the distributive property of multiplication, saying that if you have a constant times a sum, you can distribute that constant and multiply it by each term and then add them. Okay, but what we're going to be doing in our problems is we're frequently going to be just pulling the constant out front. Okay, so we can pull the constant out front when we have a constant times a function. The second property says if you want to add up a sum or a difference, you can add up each piece separately and then add or subtract them. This is just coming from the fact that we can add in any order we want. So we could add the A's and B's individually and then add those together, or we could add all the A's, add all the B's, and then add those sums together. All right, I've got 4 summation formulas now on the board. And these are formulas that are going to tell us how we can find various sums without actually having to add all the numbers together. So in my very first examples, when I introduced the idea of this sigma notation or summation notation, I gave you examples that had like 5 or 6 numbers. And so it wasn't horrible to just add the numbers up by hand or even in a calculator. But imagine we want to add up 1,000 numbers. I don't want to have to take the time to put that into my calculator, adding up 1,000 numbers. And so we've got some formulas that tell us how we can add up some special cases of sums. These are formulas that you definitely don't have to memorize. I would definitely put them on a note sheet before you take any type of quiz or exam. But in terms of your future math classes, you definitely will not have to have these formulas memorized. but you will need to know how to use them. And so let's just look at this first one, top left. This one is saying if you add up a constant, okay, so that C stands for constant. So if you add up a constant from 1, so starting at 1, ending at n, you will always get the constant times n. And so I have an example of that shown in blue. If we add up the number 3 from 1 to 7, we're going to get 3 times 7, which is 21. And if you think about it, maybe it kind of makes sense. What this means is you're taking the number 3, you're adding it up 7 times. Well, that's the definition of that multiplication. 3 times 7 is the same thing as 3 plus 3 plus 3 plus 3, 7 times. All right, so that's our first formula. When we have a constant, we get a constant times n. Second formula says if we add up I, and again, the thing to really notice here is notice that this formula says you have to start at 1, and if you end at n, here's our formula. We get n plus 1 divided by 2. So an example would be if you want to add up I from 1 to 10. So what you're trying to do is you're trying to add 1 plus 2 plus 3 plus 4, etc. until you get to 10. Using this formula, the 10 is the n, so you should get 10, and then n plus 1 would be 11. So 10 times 11 divided by 2, that gives us 55. And then we have formulas for I squared or I cubed. Notice all of these formulas, you have to start at I equals 1. And so I have written down in blue an example of each of those. So if you want to add up I squared from 1 to 10, so now you're adding 1 plus 4 plus 9. So you're adding up squares of these numbers. You will get, let's see, the formula says n, 2n plus 1, n plus 1 over 6. And so I just plugged 10 in for the n's. I got 10 times 21 times 11 over 6. And I put that in my calculator and got 385. And then finally, if you want to add up cubes, the formula is n squared, n plus 1 squared, divided by 4. I have an example written down in blue on the bottom of the screen. Okay, so we're going to be using these summation formulas to find sums. Again, notice all of them start at I equals 1. So they all only work if you're starting at I equals 1. So let's try to use a combination of those properties that I gave you with the summation formulas to find the following sum. All right, I don't want to write out all 35 numbers that I'm adding. I want to try to use those formulas. So we have a property that says if we have a sum or a difference, we can deal with each term separately. So I can find the sum of the 5i squared first, and then add that to the sum of 1. So you can do each piece in the sum or the difference separately. And then when you have a constant times a function, that constant 5, we can take that 5 and pull it out front. All right, so I've used my properties here. And now the advantage of doing this is I have an I squared. We have a formula for that. And then we're just adding up a constant, the constant 1, and we have a formula for that. So the I squared formula, I have that one written down in orange. It was the n, 2n plus 1, n plus 1 over 6. I plugged in 35 for n, and I have written down on the screen what I get when I use that formula. And notice the 5 is still there, so we're going to get 5 times whatever we get when we plug 35 into that formula. And then for the second term in the sum, the 1 is a constant, and so I'm using this formula I have written down in pink. If you want to add up a constant, you take that constant which is 1, times n, which is 35. And so I'm just going to put all of this into my calculator, see what I get. I got 74,585. All right, let's see if we can find the sum from I equals 21 to 120 of 4i. And so we have a problem here. I don't know if anyone notices what that problem is, or how is this problem different from the one I just did. The difference is the formulas I have given you only start or only work if I starts at I equal 1, but we're actually starting our sum at 21. So we're starting with I equal 21 and then going up to 120. And so how can we deal with that? Well, we're just going to have to use the formulas twice. So again, the formulas only work if you're starting at 1. So I'm going to add up from 1 to 120, and that's going to be too big. If I add up from 1 to 120, I'm including extra numbers in there because I actually want to start at 21. And so then I have to remove or subtract those extra numbers. And 1 through 20 are my extra numbers. So I want to start at 21. So I'll add from 1 to 120, and then I'll subtract the sum from 1 to 20, and I'll be left with the 21 to 120. So I'm just going to have to use my formula twice. All right, we can pull the 4 out front, or you can just think of it as the 4 stays there, the 4 doesn't go anywhere. So there's my 4. And then for each of these, I use the formula. The formula for I have it written down in orange. It's that n plus 1 over 2. And then I just used 120 for the first one for n. I used 20 for the second one for n. Put all of that into my calculator. And I ended up getting 28,200. All right, let's do one more example of using these formulas, and then eventually we're going to connect this to an area problem. So let's find the following sum for n equal 10, n equal 100, and n equal 1,000. All right, so I'm going to show you a couple different ways you can do this. We can start by let's just plug in 10 for n, do the work. And then we can plug in 100 for n, do the work. Plug in 1,000 for n, do the work. All right, so if I replace the n's with 10, I have the sum from I equals 1 to 10 of I divided by 10. Now I'm going to pull the constant out front. Technically this is a 1i over 10, and that's why the constant there is a 1/10. So I pull the 1/10 out, and I'm just left with the sum of I. And we have a formula for that. Our formula for I was the n plus 1 over 2. So here's my constant 1/10. Then I plugged into the formula for I did all the math, and got 5.5. We could do the same thing for 100. Replace the n with 100. So now we have the sum from I equal 1 to 100 of I divided by 100. Pull the constant out front. Once again, this is a 1i over 100. So 1 over 100 is my constant. Then use my formula. I have my constant, which is 1 over 100. And the formula I'm talking about is the n plus 1 over 2. That gave me the 50.5. Now, we would just have one more. We'd have to do this for n equal 1,000. But I do want to show you that we can actually do the work with the n's. So we do all the work leaving just that n there, and then plug the numbers in. So slightly different way of thinking about this problem. So we could plug the ends in later. And so what I mean by that is if you look at the original problem, right up here, I equals 1 to n of I over n, you could pull the constant out front, and the constant is going to be 1 over n. So in these sigma problems, in these summation problems, the I is always the variable. So that means that 1 over n is the constant. And then we're adding up I. Then I could use my formula. The formula for adding up i's is n plus 1 divided by 2. I could even simplify this. I could cancel some n's out. And I'm left with n plus 1 over 2. So I could do the work with the sigma notation and then plug the n's in, and I should get the same answers. Notice if you plug in 10, you get 5.5. You plug in 100, you get 50.5. You plug in 1,000, you get 500.5. All right, so with the rest of this video, we are going to switch gears and we are going to talk about an area problem, and then eventually we'll try to connect area to our sigma notation. So what we're going to be focusing on in the next couple sections is how do we find the area under a curve? And so what I'm talking about is how do I find the area between the x-axis and a function? And so I have graphed in red the function f of x equals 9 minus x squared, and I want to know the area between that curve and the x-axis from x equals 0, and it says to x equal 2. So I have shaded in orange the region that I'm trying to find the area of. Area between the function and the x-axis from 0 to 2. We are going to start by just estimating this area by dividing the region into rectangles. So this problem says use 4 rectangles. And so what that means is I'm going to divide this orange region into 4 regions of equal width. So I just cut it in half, and then I cut those in half. So I've got 4 regions of equal width. And then it says with left endpoints. And so what that means is after I divide my region into 4 pieces, for each of these rectangles, I go to the left side of the rectangle. So I go to the left side of the rectangle, and wherever that hits my function, that's how I draw the height of that rectangle. Okay? So for the second rectangle, we move to the left side of the rectangle. We go up. Once we hit the function or the red curve, we stop. And that's how I draw the height of my rectangle. So I can see that this is going to give me an estimate, but it's not going to be very accurate. You can see some of the rectangles, all of the rectangles are hanging over the region. We're going to get an overestimate here. Our answer is going to be a little bit bigger than the actual answer, but this is a good starting point. All right, so first of all, what is the width of each of our rectangles? Well, I can actually see in the picture that each of them has a width of 1/2. And we're going to call that width delta x. Just use delta x, change in x for width. And so if it wasn't clear to you by your picture that the width is 1/2, another way you could do that is you could say, well, this is a region with a length of 2. From 0 to 1 has a length of 2. And then there are 4 rectangles. So I'm going to divide 2 by 4. 2 divided by 4 is 1/2. So 2 units divided into 4 rectangles. Each rectangle has a width of 1/2. Now if we want to find the area of a rectangle, we have to take length times width, or base times height. So I have to figure out, well, what is the height of each of these rectangles? And I can actually see on my picture that the first rectangle has a height of 9, But what if I couldn't tell on my picture? Well, that first rectangle, if we're using left endpoints for the first rectangle, the left side is at x equals 0. So then I could take 0 and plug that into my function right here. So 9 minus 0 squared gave me 9. So the height of the first rectangle would be 9. The second rectangle, so if you are at the second rectangle and you go to the left side of the second rectangle, you're at 0.5. So we can take 0.5, plug that into our function. 9 minus 0.5 squared should be 8.75. Rectangle number 3, if I move to the left side, I'm at x equals 1. So plug 1 into my function. 9 minus 1 squared is 8. And then finally, that last rectangle, if you move to the left, you're at 1.5. Plug 1.5 in, you get 6.75. And so now we're finding the area of 4 rectangles. So we can just take the base times the height, or the length times the width for each one, and then add them together. So in other words, I'm going to take 9 times a half, plus 8.75 times a half, plus 8 times a half, plus 6.75 times a half. I'm going to put all of this into my calculator, and I got 16.25. So again, this is just an estimate, and it's actually going to be an overestimate. We can see from the picture that the rectangles are actually go outside of the region we're interested in. All right, but this is a good starting point. And so now let's do the same thing, except let's use 4 rectangles with right endpoints. Okay, so exact same problem, same region we're going to look at. The only difference is I want to know what would I get if I had used right endpoints instead. All right, so what does that mean if we're talking about right endpoints? It means for each rectangle, you move to the right side. So for this first rectangle, the right side is at 0.5. And so I go up until I hit the curve, and then I draw the top of my rectangle. So for each of these rectangles, you move to the right side, you go to the right side, and then where that x value on the right side hits your function, that's how you draw the top of your rectangle. So if we use right endpoints, the width, or the delta x, hasn't changed. We still have a region with a length of 2 divided into 4 rectangles. 2 divided by 4 is a half, so the width is still a half. The thing that's changed is the heights. The heights of these rectangles have now changed because the right side of the first rectangle is now at 0.5. And the right side of the second rectangle is at 1. The third one is at 1.5. And the right side of the last rectangle is at 2. So I'm going to take those numbers. I'm going to plug them into my function. So just like before, plug those into my function. I have written down on the screen what I got when I put that into my calculator. Again, plugging into the 9 minus x squared. And then finally, area, base times height. And so last time I just did the 0.5 times each one separately and then added them together. You could also just add the heights and then multiply by 0.5. That's kind of the distributive property. That would work as well. So I decided to just add up the heights and then multiply by the width, and that would give me the total area. I got 14.25. Now this time my area is an underestimate. I can see by my picture the rectangles are actually under the region, but at least I know now the area is somewhere between 14.25, and I think we got 16.25 in the previous example. Now let's see, before we do that, one more comment here. One way that we can make these areas more accurate is if we could use more rectangles. So I only used 4 rectangles. If I used 10 rectangles, my area would be more accurate. If I could use 1,000 rectangles, it would be even better. And so we don't want to have to do these computations for huge numbers of rectangles without having some kind of shortcut. And so that's why, here we go, our goal is going to be to write these area computations with sigma notation. So if we want to add together lots and lots of rectangles, we'd really like to be able to do that with our sigma notation. And so that's the next thing I want to practice, is how do I actually write an area computation using my sigma notation. All right, well, here's how. Let me try to explain what I have on the screen. So first of all, we know that the area is going to be the height times the width, and we're going to have to add those areas up. So I have the sigma to indicate I'm adding, and I'll be adding from 1 to n, where n is the number of rectangles. Okay, so we're adding up however many rectangles we have, height times width. The width is what we call our delta x. Okay, so the width is our delta x, this right here. There's a formula for how we found width in the previous problem. We basically took the length of the interval, so from b to a would be b minus a, so we took the length of the interval and we divided it by the number of rectangles, and that would give us the width. And then the height of our rectangles, is going to be a y value. We got the height by plugging numbers into our x values. We got the heights by plugging numbers into our function, so our f of x. And the numbers that we plugged in, and this is a formula that's going to work for right endpoints, but I'm only going to ask you to do sigma notation for right endpoints, okay? So what this is basically saying is we start at A and we add 1 delta x for each rectangle. So we start at the right side and then of our interval, start at the right side of the interval, and then we go over 1 width, and that's how we get the height of our first rectangle. When I equals 2, we go over 2 widths, and there's our second rectangle. If I is 3, we go over 3 widths, there's our third rectangle, etc. All right, important thing though is I have a formula right here that tells you how we're going to find the height of our rectangles and write it as a function of I. All right, so let's do some examples. Let's see if we can use the information from this slide to try to do some examples. Express the following using sigma notation. Don't compute the areas. Okay, so all we have to do is figure out what is the formula going to look like with our sigma notation. So the very first thing I would do is find the delta x. And so our formula for delta x said we're going to take b minus a, so we're going to take the length of the interval and divide it by the number of rectangles. So we have an interval that goes from 0 to 4, that has a length of 4. We are using 10 rectangles, so we're going to divide by 10. 4 divided by 10 is 2/5. So the width of my rectangles, my delta x, is 2/5. Now the height of my rectangles, I've used the formula I just gave you. The formula I gave you said you do f of a, and so a was, I guess, the left side. I wonder if I said that backwards in the other slide. I'm sorry if I did. But the starting point, I guess that's the left side of our interval. So our interval starts at 0. So we take 0 plus delta x, which is 2/5, times I. So there's my f of a plus delta x times I. And that's the same thing as f of 2/5 I. So to get my height, that means I have to take the 2/5 I and plug that into the function I have circled in blue. So I replaced both of the x's with 2/5 I. That gave me 2/5 I squared, that's the x squared, plus 2/5 I, that's the x. So this is an expression for my height. The 2/5 is my width. And so then I just have to write, we're going to take height times width and put that into a sigma. So my area is going to be the sum from 1 to 10, stopping at 10 because that was my number of rectangles, of my height, which is over on the right side of the screen, times my width, which is 2/5. And so that's how I would express in sigma notation how to find the area under x squared plus x from 0 to 4 using 10 rectangles. You don't have to go any further with this and simplify it. Really, the point of these problems is just putting together the various pieces and trying to get comfortable with writing area using sigma notation. So let's try another one. Use 20 rectangles, so n is 20, with right endpoints to estimate the area between the x-axis and the curve f of x equals x cubed from 1 to 3. So the first thing I'm going to do is find my delta x. So I have to take the length of my interval from 1 to 3, or 3 minus 1 is 2. So we're looking at a region with a length of 2. We're dividing it into 20 rectangles. So 2 divided by 20 is 1/10. So there's my width, or my delta x. My height is f of a. A is 1. We're starting at 1. F of a plus delta x. Delta x is 1/10 times I. All right, and so that formula is always going to give you your height. F of, that's my A, and then plus, see if I can write that, delta x times I. And so what I'm going to do now is I'm going to take the 1 plus 1/10 I, and I'm going to plug that in for x into my function. So that gives me 1 plus 1/10 I cubed. And then finally, I'm going to put all this together into my area formula. Area is going to be the sum from 1 to 20, because there are 20 rectangles, of the height, which is that expression cubed, times the width, which is delta x. So there's my expression for area. All right, let's do one more. Feel free to pause if you want to try this one on your own. But we are going to use 8 rectangles to estimate the area between the x-axis and y equals 3x squared from x equal -1 to x equal 3. So let's find the delta x first. 3 minus -1 is 4, or you could think of it as -1 to 3 is 4 units, dividing into 8 rectangles. 4 divided by 8 is a half. So there's my width, my delta x. My heights are going to be f of a. A is -1, plus delta x, which is a half, times I. So I'm going to take that expression, -1 plus a half I, and I'm going to plug it into the function 3x squared, plugging that in for x. Finally, I put all this together using my sigma notation, and I'm going to get the sum from I equal 1 to 8, because there are 8 rectangles, of the height, which is the 3 minus 1 plus a half I squared, and then times the width, which is our delta x, or a half. All right, that is it for this lesson. I always use I's when I'm dealing with sigma notation, simply because that's what our textbook does. It's possible to use other letters, so you might see sigmas that have J's. It works the same way. It's just using a different letter, just like using, I don't know, an N instead of an X. But please, if something's unclear about that, if you see one with J's and you don't understand, feel free to ask me about that. Send me an email. But that's it for this lesson. Let me know if you have any questions.